Let's look at an example of a tricky integral that comes up that involves some trigonometric functions. So we're going to be looking at this example not just to have a new type of trick for integration, but because tricky integrals involving trig functions are actually pretty common in applications, in some geometric applications, but also especially in physics. In physics, it's pretty common to have things moving in what's called harmonic motion, which basically means sinusoidally. And in that case, you get lots of combinations of sinusoidal functions, which gives you powers of sines and cosines and other things. So it's a good idea to have some tricks up your sleeve to be able to integrate those sorts of functions. Here's another example where we're going to end up with a power of a trig function as our integrand. So let's find the volume obtained by rotating the region enclosed by the graph of sine, x equals 0, x equals pi, and the x-axis. And we're rotating around the x-axis. So that's going to look like this. So here's the first part of the graph of sine, and we're rotating around the x-axis like this. Since it's the graph of sine, we would really rather slice this region vertically rather than horizontally. We could slice it horizontally, but we'd have to do some very careful thinking about inverse sine functions to get it right. So slicing it vertically, we get one slice for every x value. And since our variable axis, our independent variable axis, and our axis of rotation are parallel, we're going to end up with washers like this. Or really disks, I guess, since there's no hole in the middle. So we should integrate from 0 to pi just the area of one of these disks, which is pi r squared dx. So this is the volume. And the radius of this disk is just the height of the function. So what we need to square here is the function, which is sine of x dx. So we need to come up with some way of integrating from 0 to pi, pi times sine squared x dx. And there's probably you can't just guess an antiderivative, right? We know that the antiderivative of sine is negative cosine, but I mean, what about sine squared? We just don't know one off the top of our heads. So we're going to have to come up with something else. And one thing that you always need to keep in mind when you're working with trig functions is that there are all of those trig identities that you might need to use. And there are lots of different trig identities, but let's concentrate on identities that have a sine squared in them. Well, cosine squared plus sine squared equals 1 is maybe the first one that comes to mind. But using this won't really help. I mean, we could rearrange this to get sine squared x equals 1 minus cosine squared x. So this is true, but if we replaced our sine squared in our integral with 1 minus cosine squared, we're just turning a sine squared into a cosine squared, and we don't know the integral of cosine squared any more than we know the integral of sine squared. So using this Pythagorean identity, it's not wrong, but it's not helpful either. So let's keep looking for different ideas. Another identity that has sine squared in it is one of those double angle identities. So sine squared x is equal to 1/2 1 minus cosine 2x. This is one you've probably seen before, but maybe you haven't used it in a while, so hopefully this refreshes your memory. This identity is going to turn our integrand that has a square of a trig function into just a single power of a trig function. And that seems like a good thing. We know the antiderivatives of first powers of trig functions better than we do second powers of trig functions. So this seems promising. So let's go ahead and use this identity. So integral from 0 to pi. There was the pi that we started with. We're going to get a factor of 1/2, so let me put that under the pi here. And then replace sine squared with 1 minus cosine 2x dx. All right, this looks pretty promising, so let's move the pi over 2 outside integral from 0 to pi 1 minus cosine 2x dx. And now we can just integrate each piece. So pi over 2 times antiderivative of 1 is x minus, and then antiderivative of cosine 2x. You might need to do a little u substitution to handle the constant in here. But what you're going to get is, I think, 1/2 sine 2x. So this is from 0 to pi. Okay, and now we can plug in our bounds. So pi over 2 times, so when we plug in pi, we get pi minus, and then sine of 2 pi is 0, minus, and then plug in our bottom bound, we get 0 minus 0. So this whole thing turns into pi squared over 2. All right, so we were able to compute that volume because we use this double angle identity right here to handle this power of sine. So you can imagine that if other trig functions showed up, we might need different double angle identities. So let's just review the double angle identities. There are 3 of them. There are identities for the other trig functions, but these are the ones that are sort of common. These are the ones that are frequently used in situations where powers of trig functions come up. So there's the one for sine that we just used. That's this one. The identity for the double angle identity for cosine squared looks basically the same as for sine squared, except there's a plus here instead of a minus. And if you have a product of sine and cosine, you can turn that into 1/2 sine 2x. So let's look at one more example where we can use these identities. Let's find the integral from 0 to pi over 2 of cosine to the 4th x. So, well, we don't have an identity for cosine to the 4th, but cosine to the 4th is cosine squared squared. So we can use the double angle identity for cosine squared on the inside of these parentheses here. So integral from 0 to pi over 2 of, so the identity for cosine squared was 1/2 1 plus cosine 2x. Okay, all squared dx. Let's move this 1/2. So this squaring is going to make this 1/2 into 1 over 4, and let's move that outside the integral. Integral from 0 to pi over 2. Okay, now we need to square 1 plus cosine 2x. So that's 1 plus 2 cosine 2x plus cosine squared 2x. Okay, so we've made progress because, right, we started with a 4th power of cosine, and now we're down to just a 2nd power of cosine. But, you know, since we do have a 2nd power of cosine, we need to use that identity again. So 1 over 4 times the integral from 0 to pi over 2 of 1 plus 2 cosine 2x plus, and now another copy of the double angle identity, so 1/2 1 plus cosine of, now the double angle identity, it takes whatever you had inside cosine squared and it doubles it. So the double of 2x is 4x. Okay, and let me get all my parentheses here. And now we can integrate piece by piece. So 1 over 4 times antiderivative of 1 is x plus antiderivative of 2 cosine 2x is sine 2x plus 1/2 times x plus 1 over 4 sine 4x. Okay. Okay, now we need to plug in our bounds. When we plug, oh, this is from 0 to pi over 2. when we plug in pi over 2, right, we get a pi over 2 from this x here, plus sine of pi is 0, so this part goes away, plus 1/2 times pi over 2, plus, and then this sine part also gives us 0. Okay, and then when we plug in our bottom bound, 0, everything gives us 0. So it looks like altogether we have, let's see, pi over 4 plus pi over 2 is 3 pi over 4, times 1 over 4 is 3 pi over 16. I hope I did that arithmetic right. Okay, so you can see if you have some combination of powers of sine or cosine, you can use a double angle identity, or several double angle identities possibly, to reduce those powers down until you have just single powers of your trig function, and then you can integrate normally.